I'm Joey.
And I'm Freeman. We are here today to present to you our prototype model of the embedded system controller for an irrigation system.
If you find the information is going too fast, please feel free to pause or slow the video down. For this presentation, we'll be going through a high-level block diagram of the prototype to show how the MCU connects with external devices.
Then a brief look at our schematic diagram to show how all components, the buffers, the microcontroller, peripherals, devices, and etc. are physically connected.
Afterwards, we'll move on to a software flowchart to explain at a high level how the code for the microcontroller runs.
Finally, a quick energy cost analysis on the best case 24-hour scenario of the reservoir system when it runs.
In this block diagram, we can observe how all our devices connect to the STM Nucleo F401RE microcontroller.
On the right side are all the devices that require a voltage step-up from 3.3 volts to 5 volts. This step-up is achieved using the CD74HCT541 digital buffer. Devices that require the step-up in voltage include the timer/BCD board that we created back in Lab A. This uses 8 GPIO outputs from the MCU.
Another device is the RGB LED, which uses 3 GPIO outputs. The servo motor also uses the step-up buffer to step up its PWM signal from the MCU's timer 2 channel 1 to 5 volts.
The DC motor on the left has its own dedicated controller IC, the L9110, to feed it with the PWM signals from the MCU timer 3 channels 1 and 3.
The MCU's USART_RX signal is stepped down from the computer by the CD74H4050 buffer. The RPM speed sensor output signal, which uses a GPIO external interrupt, is also stepped down before reaching the MCU.
The potentiometer feeds into the MCU's ADC channel 9, while the US100 digital distance sensor uses the MCU's USART TX and RX on the MCU's USART 1 to receive a trigger and send a echo signal, respectively.
Next is the schematic diagram to show the lower level connections of the MCU's peripherals and devices. CN7 and CN10 are the Nucleo's morpho connectors.
From top to bottom and left to right, we start with a few decoupling capacitors for the power sources from the microcontroller. And then there's the motor controller and the DC brush motor, as well as the US100 distance sensor.
Then, it's a pair of the CD74HCT541 buffers connected to the servo motor, the RGB LED and the timer BCD board, and a pin to power the timer board. Any unused inputs are set to ground while outputs set to no connects.
Next is the CD74H4050 buffer used to step down the RPM sensor and the USART RX signals. Beside that is the potentiometer, and beside that is a 2-pin header to connect an external 5-volt power source. Note that the 5-volt external is used to power the servo motor and the DC motor, as well as all the buffers have accompanying decoupling capacitors.
To briefly go over this flowchart, we start off in setup mode, where we wait for user inputs and for the blue button to be pressed.
Then we go into the run mode, where depending on the current time and the start-end times chosen by the user, we'll either, if yes, run the DC motor at the specified speed, set the motor to a set position, and set the LED to a certain color. Or, if no, turn off the DC motor, set the servo motor to a default position, and then turn off the RGB LED altogether.
Afterwards, we measure the distance with the US100 distance sensor. If the distance is 0, that means our reservoir is empty, and we'll go into the ending sequence where the RGB LEDs flash in a sequence and motors are turned off before completely ending. In other words, it waits for a reset.
If it's not 0, then we will continuously check if we've reached 6 real seconds or not. If not, we will go back into the run loop to continue our checks. If yes, our current time will go up by 1 hour. If our current time reaches 24 hours, it gets reset to 0 hours. And every time the current time gets incremented by 1 hour, we will print to the terminal the current state of the system, including the time, the zone, the RPMs, and etc.
Finally, we reach the operational costs. With the given information about min and max RPMs, and the energy it takes to reach those RPMs, we have derived this table to show the speed at which each zone finishes if it runs at a minimum or maximum RPM.
We then calculated the best case cost scenarios for both energy tables provided. For the best case scenario, we assume the 24-hour sequence is either during a weekend or going into the weekend, and will always start at 11 p.m. We broke down the cost for the minimum and maximum RPMs to find a range of costs.
Comparing the two, it seems that the ultra-low overnight provides the lower cost for our 24-hour period, using the minimum RPMs for all zones at $247.50.
And that's the end of our presentation. We'd like to thank you for your time, and we really appreciate this opportunity to demonstrate our prototype, thought process, and analysis. Thank you.